Presenting DRaM-LHM, our iterative 6-DoF camera pose estimation framework, which has just been accepted by ICCV this year. But for this talk, rather than jumping directly to this solution, I want to take a different route in this talk. I want to start from its algebraic foundation, the adjugate quaternion, which developed by Dr. Andrew Hansen, and I will show briefly how this algebraic framework comes from, and briefly explain how this adjugate form can be used as a deep learning representation, which actually attributed of my ICCV 2023 paper. Then I will start to discuss this year's ICCV, and instead of representation, this algebraic framework becomes a parametrization. Then we plug it into the rotation matrix and solve a least square optimization problem without any learning process. Yeah. So we can start to introduce this adjugate quaternion. And to introduce this, I want to introduce two classical problems. The first one is the point registration problem, which solved by Horn in 1983. So in this problem, the goal is to align two corresponding 3D point sets, the xi and yi, as the least square optimization objectives presented here. And by expanding this objective, you end up with this form in which the only term corresponding to rotation is the last term. So this problem becomes maximizing the last term, which is the cross term between xi and yi up to a unknown rotation. And with some fundamental linear algebra, we know that we can collecting all those terms, and this optimization becomes maximizing the trace of this rotation and the corresponding cross terms. Then we can further parameterize the rotation by classical unit quaternion, and with collecting corresponding quadratic terms of quaternion components, this trace becomes the quadratic form with the quaternion and the symmetric matrix, which included by the data x and xyz from your input point sets. And finally, we end up with finding the optimal rotation by giving the dominant eigenvector of this symmetric matrix. So the second classical problem I want to introduce is the frame alignment problem, which solved by Bar-Isaac in 2000s. So this problem differently, we are given a non-rotation, which represented by its three orthonormal axes, x, y, and z. And we try to find the best rotation parametrized by a quaternion, which align to it. So even though the data structure looks different, here we have x's, xyz instead of point clouds, but the algebra underneath is exactly identical in the Horn's RMSD problem. The objectives again reduces to maximize the trace expression, and once we collecting all corresponding terms of quadratic quaternions, we end up with find the optimal rotation by finding the dominant eigenvector of a symmetric matrix. So now as I introduce those two classical problems, we find by any means we reduce this rotation estimation problem as the eigenvector problem, which we need to solve by this characteristic polynomials. And this equation can be solved once we have the eigenvalue of this symmetric matrix. This equation can be solved by its adjugate or cofactor matrix. which satisfy these characteristic polynomials. And with a singular, with this symmetric matrix as a singular matrix, its form must be the order product of this column vector. And we know that this symmetric 4x4 matrix encodes the rotation of the optimal rotation, encoded the optimal rotation of this data or the frame alignment problem. So here, by introducing this 4x4 symmetric matrix, the adjugate quaternion, we can use this representation in a deep learning context. So here is a simple illustration which adapted from Joe, etc., from CVPR 2019. And this illustrated that given by any input signal like viewpoint estimation by input images or the 3D point registration by input the 3D point cloud, or very general like post estimation or post branch prediction in a feed-forward dense reconstruction. Whether the deep learning task is supervised or unsupervised, the goal is almost always to predict the rotation under this neural network. But finally, you must let the rotation lies on the SO3 group or S3 manifold. However, in practice, the neural network produces a row matrix or any pose representation that does not automatically satisfy the rotation constraint. So therefore, we always need the rotation correction steps for which you project the output from the neural network back onto the S3 sphere or SO3 Lie group. Most popular method like Joe 60 or Amish SVD method treat this rotation correction as a projection step. For example, Joe's 60 representation predicts the two columns and uses Gram-Schmidt to recover the third column. And Amish's SVD method add extra layers to factorize the matrix to project it in the nearest rotations. So this method enforces the orthogonality after prediction, meaning the network itself cannot learn the rotation structure, and it imposed afterwards. So different from the this projection-based rotation correction, our representation goes back to the algebraic foundation. Like I introduced the Horn and Braisak, they solve this rotation alignment problem analytically and encoded in this 4x4 symmetric matrix. So the key difference is the adjugate quaternion formulation already encodes the SO3 algebraical constraint, which is a unit norm and orthogonality inside the representation itself, rather than enforcing them after the external projection. So, and from our experiment, we saw that the neural network itself can actually learn the rotation structure instead of just being forced back to SO3 after prediction. So on the right-hand side is our preliminary results from our ICCV 2023, in which we use a simple point net backbone and regress the point clouds to the ground truth orientation. And you can see that the adjugate quaternion representation yield a lower error and significantly more stable than the learning based on the 60 representation. Yeah, so up to here is the rotation correction part in the deep learning context. And after that, I can introduce that on top of the adjugate quaternion as a representation, it can also be a parametrization. First, I will introduce how this 4x4 symmetric matrix can become variables to parameterize the rotation matrix. So from our previous introduction, we know that we have this symmetric order product of Quaternion, which actually 10 unique quadratic terms of unit Quaternion. And right now, instead of regarding it as a quadratic term, we now regard it as monomials or single variables, which we can denote as Qij. And to reduce those 10 monomials back to 3 degree of freedom of rotation, we need 7 algebraical constraints. The first one is pretty straightforward, which is a unit norm constraint, and the summation of all Qi will equals 1. And the other comes from the rank 1 matrix of this adjugate matrix, in which all 2x2 minors vanishes and give extra 6 constraint for any I smaller than j. So by those constraints, we now can use those monomials as parametrization and to represent the rotation in the same way that the unit quaternion does. However, unlike the original quaternion parametrization, where each matrix entry contains quadratic terms, in this formulation, each entry is linear as the adjugate variables as we just introduced. Here I listed all constraints and the parametrized rotation matrix here on the right-hand side. Yeah, by introduce all this algebraical background, now I can introduce, we can move to the real optimization problem corresponding to the to this year's contribution, the 6th camera pulse estimation problem, which this problem is also well known as perspective endpoint problem. So to introduce, I first introduced the definition of the PNP problem. The PNP problem estimates the camera absolute pulse from non-3D points and their 2D image projections given by calibrated intrinsic parameters by minimizing projective geometry objectives. So the PNP problem can be solved either analytically or iteratively by minimizing one of 3 standard objectives listed here and illustrated on the right-hand side. Their reprojection error in orange, which actually is the pixel Euclidean distance on image space, and the Z prime error, which can which highlighted in blue can be regarded as the depth scaled reprojection error, and also the collinearity error, which is the objectives we've used in this project and we'll introduce in detail later. So by any means, in all PNP formulations, you reduce objectives to this least square objectives as a function of rotation, unknown rotation, and translation up to a given input of 3D points x and their projection u. You can solve this either in a closed form or analytically or iteratively. For a closed form solution, you either linearize the problem like EPMP by mapping the input data into a subspace, but this will break down in some planar case or symmetric case and make the algebraical formulation ill-posed. Or you can directly solve the higher order polynomials exactly like the direct least square method. This will be algebraically heavy and numerically unstable, like DLS use Cayley-Gibbs Rodriguez representation, which will be redefined at 180 degrees. So you can also solve this by iterative refinement method like LHM, but it assumes good initialization and its performance relies heavily on the starting point. Also, the iterative refinement can be computationally expensive. Different from all those methods, our approach is leverages an advanced algebraic framework, the adjugate quaternion we just introduced for initialization, and iteratively minimize the collinearity error by LHM iterative scheme. So here's our an overview of our method. We first start by incorporating 3D and 2D data through orthographic projections for initialization, and then iteratively refine the solution use LHM refinement. Our method begins by solving the orthographic projection error analytically by using the adjugate variables we just introduced. Here, P is projection is the first two rows of a rotation matrix, because in an orthographic projection, the depth becomes arbitrary. So we can ignore the third row of rotation matrix. And the T12 is the first two components of the translation vector. And the lowercase p and u are the 3D data and the corresponding projection 2D data. So we solve these least square polynomials analytically, and with expanding this least square equation, we can get a polynomial equation with the variables of adjugate variables, and its coefficient are 3D and 2D data x, y, z, and u, v. For convenience, we define a data matrix, collect all those terms, and present it here on the right corner. And you will see how convenient it is shown in our solutions. So here is the core of our method, the determinant ratio matrix method, which actually is the closed form solution of the objective we just showed in our last slides. And by parameterize the rotation matrix, first two rows, we end up with these orthographic reprojection errors, and it can be expanded as polynomials up to degree of 2 of adjugate variables. And to find the optimal conditions, we need to take derivative respect to all 10 adjugate variables, and in addition to and with actual constraints of the adjugate quaternion. So we actually only include one unit quaternion constraints in our solutions, but our solutions fulfills all constraints automatically for all 7 constraints. For details, you can read Andrew's original work and derivations. So here I will just show how this solution can be clean, can be presented clean in the determinant ratio matrix. So to solve this optimal rotations, we end up with the first rows, and those first rows can be expressed as a determinant ratio of the submatrix of the data matrix I introduced in the last slides. And I presented here again on the top right corner. And the third row of the rotations can be directly obtained by the cross product of the first two row, and together they form the estimation of the rotation, which played as played as initialization for the PNP problem. So here's an example of determinant ratio of matrix, in which the dxyz is determinant of the submatrix of top left, and which plays as a normalization for all entries of the rotation matrix we estimated. So after estimate the initialization by using DRaM solutions, we can start to refine our estimation and using the LHM iterative scheme. So LHM it minimizes the collinear error to solve this problem. So the so-called collinear error is actually the error measures the discrepancy between 3D scene points and their corresponding re-emitted from image pixels, and which resolved through a Gram-Schmidt-like process. Here, the VK is a unit re-vector from pixels from observation UK, and combining all those together, the collinear error can be expressed in this formula. These polynomials cannot be solved analytically under any specific parametrization. So instead of solve it directly, the original LHM solution solves this in an iterative manner, in which it uses first guess the rotation and fixing this rotation, then solves the optimal translation under this rotation. They repeat this process iteratively under the convergence threshold. So we adapt this manner but use a different initialization. In original LHM solution, it used weak perspective approximation, where the weak perspective is simply a scaled version of the homogeneous projection using heuristic constant depths, which can be illustrated here on the bottom right, in which the blue dots is 3D scene points and the perspective to the image plane, and the weak perspective approximation only scale up directly to the 3D space with constant depths. So this can be a poor assumption, especially when the 3D points are well distributed with significant depth variation. So different from this initialization, we use the DRAM solution to estimate a rotation under true projections. Although it's an orthographic projection, but it can solve the real projective scenario. And you will see how our solution provides a significantly better initialization in our next slides. So here I will present the key results, and I will briefly discuss the planar scenario and some drawback of our method. So here are our key results. The figure on the left is shows that our initialization is significantly better than LHM's weak perspective approximation. In which our initialization is robust under different level of image noise, and only slightly increasing the error when the noise is real large. And the middle figures highlights the efficiency of our method. Both the numbers of points and the number of iterations can be turned flexibly without sacrificing the accuracy. And our methods remaining comparable to state-of-the-art method like SQPNP. And finally, the right-hand side, we present a table shows that our method performs strongly on real-world dataset including TUM, RGBD, and UROC MVV, especially like under some dramatic blurring and jittering of the image, our estimation is still robust and comparable with SQPNP. So finally, it was to mention that the key limitation of our method, because the DRAM solution is a closed form solution, relies on the orthographic projections, and it will become less effective in a planar scenario. In this case, it introduced a strong geometric ambiguity. The determinant of the self-covariance matrix or the profile matrix we introduced will vanishes, which can lead to inaccurate estimates. So in our experiments, perturbating a plane with different noise level shows a quasi-planar crossover, in which DRAM becomes auto-performs a weak perspective. And in practice and productive application, we treat weak perspective as a fallback when the points are not well distributed or nearly on the planar. And combining those two schemes, our method will be robust on the almost all conditions. Yeah, finally, thanks to my advisor, Sonja Hansen from Flattery Institute, and our collaborators, the develop of the whole adjugate Quaternion framework, Dr. Andrew Hansen from Indiana University, and my co-workers, Eric Dunn from Stevens Institute. Yeah, and thanks for everybody's listening, and I open to questions. Yeah.
Thank you, Chang. That's amazing, amazing research. It seems that the audience is enjoying this talk. We have one question in the Q&A tool. I will read this. So you mentioned the solution is for the orthogonal projection. What is the effect of perspective projection on the solution? So maybe you already answered the question during the presentation. This is a question that was coming pretty early when you started.
Okay, yeah, so this actually we discussed in our paper. So orthographic projection is still a projective scenario. So it can handle most of distributed data. And the prospective condition not influence too much because you have focal length scaled the data with so the influence is very small, and practically we also show that the orthographic projection